an intake manifold that was also the cover for the tappet chamber. On engines like that, if the gasket isn't suction tight, manifold vacuum will pull oil mist into the intake ports, and into the combustion chamber it goes along with the fuel mixture.
A lot of things have changed since this film was used to train technicians. Today's automobiles are smaller and more aerodynamic. They also handle better and rely on electronics to improve vehicle performance. However, one thing has not changed: driver expectations. Customers still demand automobiles that meet high standards of performance. Today, we use the word drivability to describe driver expectations. Drivability is difficult to define, but most customers agree that a car which has good drivability starts easily, runs smoothly, accelerates quickly, operates quietly, and maintains good fuel economy. Most customers also agree that the symptoms of poor drivability include hard starting, an engine that cranks but won't run, hesitation, sag, stumble, surging, chuggle, lack of power, detonation, spark knock, cutting out, missing, backfiring, poor fuel economy, dieseling, rough idle, stalling, excessive emissions, and engine noise. This know-how reference manual, Drivability Diagnosis, Engine Mechanical, describes each poor drivability symptom. But knowing the symptoms is only the first step in correcting poor drivability. To make a car perform to the driver's expectations, you must know what can cause each symptom and how to correct it. To help, the reference manual also contains a diagnostic chart that provides probable causes and the appropriate corrective actions. One common misconception is that all drivability problems are caused by electronic engine control malfunctions. It's sometimes easy to forget that under all those high-tech controls, there is a basic engine. That's why this know-how program concentrates on the #1 requirement for good drivability: proper engine operation. Today's Buicks still rely on the basic internal combustion engine, and its operation is based on the 4 strokes of the 4-stroke cycle: intake, compression, power, and exhaust. The intake stroke starts as the piston leaves top dead center with the intake valve open. As the piston moves down, it acts as a pump, creating a partial vacuum. The vacuum allows atmospheric pressure to force the air-fuel mixture through the open intake valve into the cylinder. Because the engine acts like a vacuum pump, the amount of vacuum produced by an engine is one good indication of its condition. The air-fuel mixture continues to fill the cylinder until the intake valve closes as the piston reaches bottom dead center. The compression stroke starts with both the intake and exhaust valves closed. Now, the upward movement of the piston squeezes or compresses the air-fuel mixture in the cylinder. Just as the piston reaches top dead center, the spark plug ignites the compressed air-fuel mixture. This starts the power stroke. The combustion of the air-fuel mixture forces the piston downward. As the piston reaches bottom dead center, the exhaust valve opens, and the exhaust stroke begins. Pressure within the cylinder and the upward movement of the piston force the burn gases out of the cylinder. As the piston approaches top dead center, the intake valve opens. This is called valve overlap. It helps to purge any remaining exhaust gases from the cylinder. With the cylinder at top dead center and the exhaust valve closed, one 4-stroke cycle is completed. This cycle occurs once for every 2 engine revolutions. In other words, if the engine is running at 1,200 revolutions per minute, each cylinder completes 600 4-stroke cycles every minute. You can see that a number of very fast, precise actions must occur for an engine to operate correctly. That's why you cannot ignore engine fundamentals when diagnosing drivability symptoms. With this in mind, let's take a look at some of the common engine-related drivability symptoms and the proper approach for diagnosing them. One common drivability symptom is a rough engine idle. Suppose you come in one morning and find a car in your stall with a repair order that reads, "Engine idles rough." Of course, your first step would be to verify the complaint. But what would you do then? You may decide to try a high-tech diagnostic approach. While verifying the complaint, you notice the service engine soon light flashing intermittently, and so decide to perform a diagnostic circuit check. The diagnostic circuit check reveals a code 33 stored in the memory of the electronic control module. You know that code 33 indicates a problem with the manifold absolute pressure sensor. Before replacing any parts, however, you decide to verify that the map sensor is sending an incorrect signal. The map sensor reads over 4.0 volts. This confirms that the map sensor is sending a faulty signal. You're not sure of the next step, so you decide to consult the service manual. Since you've already determined that the sensor is reading over 4.0 volts, you decide to start at step number 2. Step number 2 instructs you to turn the ignition off, disconnect the map sensor connector, and then turn the ignition back on. The reading should be 1 volt or less, so you move to step 3. Step 3 instructs you to check for ground to the sensor by probing circuit 469 with a test light connected to 12 volts. The test light should light, and it does. The diagnostic chart indicates that if the test light does light, the problem is either a plugged or leaking vacuum hose or a faulty map sensor. The vacuum hose is not plugged and there are no leaks, so you decide to replace the map sensor. This diagnostic approach seems sound enough, but replacing the map sensor won't correct the rough idle. Why? Let's go back to step 1 in the diagnostic chart, which recommends that if the engine idle is rough, unstable, or otherwise incorrect, it should be corrected before using the chart to diagnose a code 33. So in this case, skipping the first step resulted in an incorrect diagnosis. By connecting a vacuum gauge and performing a manifold vacuum test, we would have found that low, unsteady manifold vacuum was responsible for the incorrect map sensor reading. Remember, since manifold vacuum is directly related to engine operation, a manifold vacuum test provides a good indication of engine condition. A normally operating engine will produce a steady vacuum gauge reading between 15 and 22 inches of mercury. A low, steady vacuum gauge reading is an indication of several possible problems, the most common of which is late ignition timing. Notice that the spark plug fires after the piston reaches top dead center. The result is a shorter than normal power stroke. But a low, steady reading may also be caused by incorrect valve timing, leaking piston rings, or a leaking intake manifold gasket. On the other hand, a floating or drifting needle is an indication that the air-fuel mixture is too rich or too lean, or that there is an intake manifold leak. A needle that only intermittently fluctuates indicates an ignition system malfunction or a sticking valve. A needle that steadily fluctuates or drops back indicates low compression caused by a leaking valve, a leaking cylinder head gasket, or leaking piston rings. Possibly this vacuum reading could also indicate an intake manifold vacuum leak. Additional tests will have to be performed to determine the exact cause of the problem. A vacuum leak is commonly caused by a leaking vacuum hose or a leaking intake manifold, carburetor, or throttle body. To test for a leaking gasket, start the engine and run it at fast idle until operating temperature is reached. Then, with a vacuum gauge connected to the manifold vacuum source, spray carburetor cleaner along the intake manifold and carburetor or throttle body gaskets while observing the vacuum gauge. If the vacuum gauge reading and engine idle condition does not improve, the intake manifold is properly sealed and not causing the rough idle condition. If the vacuum gauge reading increases and the engine idle smooths out, there is a leaking gasket. On large leaks, it may be possible to see the solvent drawn into the leaking gasket. However, on some engines, the lower edge of the intake manifold may not be accessible. Therefore, the vacuum leak test will probably not identify these leaks. To test for a leaking vacuum hose or vacuum system component, disconnect and plug the vacuum hoses from the intake manifold, one at a time, while observing the vacuum gauge. To make the job easier, start at the source. Most engines use a common vacuum T to supply most of the systems that use vacuum. If the vacuum gauge reading increases or the engine idle smooths out after disconnecting and plugging a vacuum hose, check for a damaged hose or a leak in the system supplied by that hose. If the vacuum leak test does not locate the cause of the rough idle condition, it'll be necessary to check for the other likely cause of fluctuating vacuum gauge reading, low compression. This is done by performing a compression test. A compression test begins by removing the spark plugs. Check the condition of each spark plug as it is removed. Spark plug condition is a good indication of the condition of each cylinder. A wet, oil-fouled spark plug is caused by excessive oil entering the combustion chamber due to worn or damaged piston rings, pistons, or valve guides, and can help identify a cylinder with low compression. Remove the air cleaner and place the throttle in the wide open position. On vehicles equipped with a carburetor, also place the choke valve in the wide open position. Next, disable the ignition system. On this engine, that involves removing the 2-pin connector from the direct ignition system module. For the procedure for disabling other types of ignition systems, see the know-how reference manual. The compression reading for the lowest cylinder should not be less than 70% of the highest cylinder, and no cylinder should read less than 100 psi. Suppose that the engine tested has compression readings of 160, 155, 105, and 155. Notice none of the readings are below 100 psi. But what about cylinder number 3? What percentage is 105 of 160? You can either calculate this or refer to the chart in your know-how reference book, which shows us that 70% of 160 is 112. 105 is below 112, so the compression of the cylinder is below the lowest acceptable compression reading. So, the cause of this rough idle condition is low compression in the cylinder and not a faulty map sensor. But before we start to disassemble the engine, a wet compression test will help determine if the low compression is caused by the piston rings or the valves. First, squirt approximately 1 tablespoon of engine oil or 3 squirts from a plunger-type oiler into the cylinder. Then crank the engine a few seconds to distribute the oil and repeat the compression test. If the reading shows a considerable increase, the low compression is caused by leakage past the piston rings. The compression reading increased because the added oil temporarily sealed the piston rings. But what if adding the oil does not increase the compression reading? Then the most likely cause of the low compression is leakage past the valves. At this point, remove the valve cover and check for a damaged valve train component. If no damage is found, the next step is to remove the cylinder head and check for a worn or burned valve or valve seat. Engine noise can be tough to diagnose. Often, engine noise is intermittent and can depend on many variables. However, engine noises can be successfully diagnosed by using the simple four-step approach. The first step is to identify the type of noise. For example, is the engine producing a dull knock or a light tapping sound? The second step is to pinpoint the operating conditions under which the noise is heard. Does it happen when the engine is hot or cold, under load or coasting, or only at certain engine speeds? For example, piston slap is most noticeable when the engine is cold and operating at medium speed. The third step is to determine the rate at which the noise is heard. Some engine noises are synchronized to the engine speed. Noises timed to the engine speed can be caused by the crankshaft, connecting rods, or pistons. Other noises are timed to 1/2 engine speed. These are usually valve train noises. The fourth step is to determine the location of the sound. If necessary, remove the drive belts to eliminate noises caused by the belts or components they drive. An engine stethoscope is a useful tool for locating engine noises. One caution, however: noises easily travel from one engine part to another. So move the stethoscope probe around to find the point where the noise is the loudest. A cylinder balance tester can also be a helpful tool when diagnosing engine noises. By canceling the cylinders one at a time, the location of certain engine noises can be identified. For example, a car is brought in with an engine noise. It is a sharp knock that is heard when operating at medium engine speeds. The noise is heard regardless of engine load or temperature. You have also determined the frequency of the noise. It is timed to the speed of the engine. This means the noise is probably caused by the crankshaft, a connecting rod, or a piston. Using a stethoscope, it is discovered that the noise is coming from the lower end of the engine. Using this information and the engine noise diagnosis chart found in the Know-How Reference Manual, you could most likely identify the source of the noise. It's probably a connecting rod knock. Fortunately, the location of the noise can be verified using a cylinder balance tester. To perform the cylinder balance test, connect the tachometer and the cylinder balance tester to the engine. Start the engine and run it at the speed at which the noise is heard. In this case, approximately 2,000 RPM. Then cancel the cylinders one at a time while listening for any change in the noise. If the knock is reduced by canceling a cylinder, the connecting rod bearing for that cylinder is causing the knock. If the noise is not reduced or reduced only slightly, the problem is not a rod bearing noise. One note, however: canceling the cylinders will cause the engine speed to drop, and this may affect the engine noise. It may sometimes be necessary to also use a stethoscope to enable you to listen more closely to the noise as each cylinder is canceled. If a cylinder balance tester is not available, The same results can be obtained using insulated pliers to disconnect each spark plug wire one at a time. Since the engine knock was reduced considerably by canceling, a connecting rod bearing is the probable cause of the engine noise. All that is left to do now is to remove the oil pan and confirm the diagnosis. Another common drivability symptom is engine cuts out or misses. This symptom is characterized by a steady pulsation or jerking. The symptom is usually more noticeable as engine load increases. First, let's talk about the quick fix diagnostic approach. This approach usually starts like this. After looking at the repair order and opening the hood, the technician notices that the car is equipped with a C-cubed-I ignition system. He's immediately reminded of a car that was in the shop a few weeks ago. It also had a C-cubed-I ignition system and a similar problem. On that car, replacing the crank sensor solved the problem. So, of course, replacing the crank sensor on this car might solve the problem and save a lot of time as well. So it's get a new sensor from the parts department and go to work replacing the crank sensor. I'm sure that you can guess the results of this diagnosis. That's right. Replacing that crank sensor did not correct the engine miscondition. It's important to diagnose drivability problems as quickly as possible. No one wants to waste time, but the quick fix approach rarely works. In this case, performing a few simple diagnostic tests first would have saved more than just time. When diagnosing a cuts out or miss condition, the reference manual indicates that a cylinder power balance test should be performed. This test can be performed quickly, and it helps narrow the problem to 1 or 2 cylinders. To perform this test, after connecting the tester and a tachometer, start the engine and increase the idle to approximately 1,000 RPM. Cancel each cylinder one at a time. Notice and record the RPM drop of each cylinder. When properly operating cylinders are canceled, there will be an even drop in engine speed. When weak or inoperative cylinders are canceled, there will be little or no change in engine speed. Cylinders that produce little or no RPM drop have either an ignition system malfunction or a mechanical engine problem. Use a spark tester to check the ignition system. If there is no spark at the tester, the ignition system is causing the engine miss. If there is spark, check the spark plug of that cylinder for cracks, wear, improper gap, or burned electrodes. Replacing a worn or damaged spark plug will often correct an engine miss. However, if the spark plug is in good condition or has heavy oil deposits, a compression test should be performed. Suppose the compression test indicates that a leaking valve is causing the problem. A cylinder leakage tester can be used to determine the exact cause of the problem. This tester pinpoints leaking exhaust valves, intake valves, piston rings, and head gaskets, as well as leakage into coolant passages. To perform the test, warm the engine to normal operating temperature. Stop the engine. Then disconnect the spark plug wires and remove the spark plugs. Next, remove the air cleaner if necessary and place the throttle in the wide open position. On vehicles equipped with a carburetor, also place the choke valve in the wide open position. Remove the radiator cap and the oil filler cap. If the cooling system is low, add coolant to bring it up to the proper level. Now, rotate the crankshaft until the piston of the cylinder being tested is at top dead center on the compression stroke. Then install the cylinder leakage tester hose into the spark plug hole and pressurize the cylinder. The cylinder leakage tester will indicate the percentage of leakage for that cylinder. 0 to 10% leakage indicates the cylinder is in good condition. 10 to 20% leakage indicates fair cylinder condition. 20 to 30% leakage indicates poor cylinder condition, and leakage above 30% indicates a problem condition. To identify the exact cause of the problem, you'll need to determine where the air is escaping. Excessive air escaping through the throttle body or carburetor indicates a leaking intake valve. Excessive air escaping through the tailpipe indicates a leaking exhaust valve. Excessive air escaping through the oil filler opening indicates leakage into the crankcase caused by worn or damaged rings, cylinder walls, or a damaged piston. Air escaping into the radiator indicates a leaking head gasket or a cracked engine block or cylinder head.
On this particular job, the gaskets were shot, so all Mac had to do was put in new ones. Then a couple of weeks after that, Junior thought he finally hit the jackpot. This engine was equipped with a crankcase ventilating valve, the standard equipment on many
Yes,
truck
things
engines
have changed since this
fumes
film
from
was
the
made.
crankcase.
However, engine performance is as important on today's high-tech cars as ever. Your knowledge of basic engine operation can help when diagnosing any drivability condition. And accurate drivability diagnosis is good business for you and for Buick.